Hello and welcome to the Orleans Virtual Meetup number 14. And you're hopefully joining us live on Skype for Business, or you can catch the recording later on YouTube. Today we're joined by John Azariah, I hope I got that right, who's going to talk to us about finite state machines in Orleans. John, everyone knows John. He's a retired MVP and now back in Microsoft working on interesting stuff with quantum computing, so hopefully he'll entangle us with some of that later. Like what I did there. And hopefully at the end we'll have 5 minutes or 10 minutes with Jacob talking about some of the event sourcing stuff I think he's done with stateless workers. So have a quick tour of some of the work he's been doing there. So I'll hand over to John, who'll give us a presentation. John, do you want to take over?
Sure. I'm going to see if I can share the screen here. All right, so this is effectively a reprise of a talk that I did at NDC London. However, I must apologize at the beginning that I don't have a fully functioning demo. So when we get to it, you'll have to excuse my waving hands, and hopefully in very short order go off and run it for yourself when you get a chance. And let's start with that. So basically the experience of everyone here in this user group is that we've actually used Orleans, so we don't really need to have an introduction to what it is and when it's appropriate to use it. However, I think because of the way in which we are currently used to using Orleans effectively as distributed C#, we kind of miss a little bit of the power and expressivity of it, and with a little effort we can actually make our experience of designing actors that do things much better. And this talk is one humble approach to actually doing that. So as Richard kindly mentioned, in my previous life I was a consultant, and on a daily basis I had to come up with new solutions to old problems and mostly boring line of business applications. I mean, anyone who's listened to Scott Lashton knows what a blobber is, a boring line of business application. And fundamentally, usually it's one of those things that takes many years to sort of get right in terms of building out its functionality, and it probably runs for much longer. And usually we have to deal with issues of success. And when you're successful, you have to scale, and that's one big issue. And capability, which is the changing business logic as companies evolve, the business evolves, the requirements evolves, and so on and so forth. And the idea is that once such changes are given to us, we want to be in a situation where we can respond to them fairly easily and so on and so forth. So the first one's usually easy to sort of sort out, relatively speaking, because you pay someone a great deal of money to come in as a systems architect, and then they sit and draw some diagrams, UML and whatnot, and then decide what system components and need to be set up, and which pieces of stuff are going to be running in the cloud and all of that, and you have some idea of how to handle scale. And then when the time comes to actually model the domain and do work associated with it, well, again, there, you can set up a fairly good team and get things going, and they will follow industry best practices and so on and build the capability that you require. However, where it all starts falling apart, as we probably all know from experience, is when the business logic starts getting changed as requirements come in, change requirements come in, and then even if you follow the industry best practices and you have the best possible system to begin with, the best designed infrastructure to begin with, I put it to you that it is actually less than palatable to try and incorporate the changes into an existing system. We're going to take a look at that in a minute. So, part of the problem is actually communication, because we are usually communicating with ourselves as developers over time. We write code that we read in the future, then we wonder what we thought we were doing when we had written this code in the past. That's the charitable view. The possibly non-charitable view is, what the hell was somebody else thinking when they were writing this code in the past? And a great deal of the source of the problem is actually the specification of intent in a clear and unambiguous way, and in a manner that allows us to actually action without having to gain a PhD in actually reading the specification. The paragons of design that have stood the test of time typically tend to have tomes of architecture design documents, and you spend a great deal of time reading them and understanding the context in which decisions were made, and that relatively reduces the agility that you have in order to deal with the system. So that is the first problem. The second problem is actually that the logic and the flow control associated with it both get interleaved in the form of the program. And even if we use, the best intentions and the best skill, there's limitations, I think, in the way in which we express our intent in code that stem from the point that this intertwining happens. Consequently, it is actually impossible to predict what is going to work in the future, and it's an exponentially greater amount of effort that you put in to try to future-proof your work. So how do you improve the system? What does a good system look like? I think it's fair to say that the things that we want to do are effectively these 3 points. We want to be able to reason about the system in a more easy way. We need to modify the system safely. And honestly, we really shouldn't have to expect somebody to rewrite the whole thing in a different language or on a different platform. We want to have a mechanism of doing this that doesn't actually impose certain restrictions on us. So with this in mind, I'm going to build a bank. Now, the problems that we're going to face in terms of building this are going to be very evident to everybody in this user group because we've all used Orleans. But bear with me, because somebody who in the future is going to read or take a look at this video wondering how do you actually use Orleans for a real-world project, this may be somewhat relevant to them. So let's assume that we have 3 business rules. A bank account has a balance of 0. You support depositing money, and we will increase the balance appropriately. And if a bank balance has a positive balance, bank account has a positive balance, then I'm allowed to withdraw from it. Now, this is a bit of a strange rule because I don't care about what the state of the bank account is after the first withdrawal. It might actually it might actually dump me into a negative state. But I'm a simple-minded bank. I'm going to allow this to happen because I don't want to have to do the arithmetic to figure out, what the final state of, say, a deposit is going to do, or what the final state of a withdrawal is going to be. I'm just going to say, if my current state is positive, then I'm going to allow a withdrawal, right? So, fairly innocuous set of rules. Yeah, I don't think anyone really has a problem with the semantic understanding of the rules themselves. So let's find the best possible way with the best intentions and the best skill, and we're going to go off and try and build a system that does this. So some code that we do might look like this. We initialize a bank account ID, and then, if the bank account doesn't exist, we create a new bank account, set its balance to 0. Then when we want to deposit, so this is the second business rule, we get the bank account, and then if it doesn't exist, we have a problem, so we throw. Otherwise, we update its balance, and then we save it. And the third one is a withdrawal, which has an extra check in there to see if the balance is greater than 0. I think without overstating the point, I hope to impose upon you that this could be done in much the way that I've described it, with the best intentions and with all the appropriate testing and so on and so forth. I don't think there are any fundamental different concerns that we're going to have that I haven't addressed in this demo so far. But then once we do this, let's assume that we have our first change request. We want to be able to close an account. And close an account means that we can't operate on it further, but we should only be able to close accounts that have a 0 bank balance. That is to say, you must settle affairs with the bank before you decide to close your account. Again, these are not unreasonable requirements that can be added to the system. But the work required to do this, I think you'll agree with me that this is at least a reasonable subset of the work that you would need to do in order to make it happen. So for example, I would have to have a property of the bank account to indicate whether it's closed. I would have to make sure that all the tests deal with the existing tests, all assume that it's a non-closed system, so I must ensure that the non-closed requirement is incorporated into that. I must add new tests for the closed case. Modify the service code to make sure that the tests pass. Add tests to verify that the close must only do stuff on a 0 bank balance. Modify more service code. Then add a test to verify that closing a non-0 bank account balance is dealt with appropriately. And then modify more service code to handle that. So this again looks like something that we would do when we do our agile sizing. When someone says, hey, here's a requirement, and then somebody would come back and say, okay, these are the things that we would need to do in order to make this happen. And all of a sudden, everything that we had designed and built has to be touched again. And usually, this happens at a time when the original team has gone home successfully after the project. You know, the party's over. You know, they've shipped the product. The super expensive systems architect has been sent off on his way. The new developers have come in to do the maintenance of the code, and now they have to deduce everything in terms of the context of their work by just looking at the existing code. And so it's not entirely reasonable that we would have a situation where we would ask a question, what happens when we initialize? If the account exists and is closed, what happens? And there's a conversation that can be had about whether there is a concept of a closed, non-initialized account. Right? Now, you can see that just the simple requirements that have been put in, which seemed very reasonable to begin with and described the business value that you wanted, weren't unambiguous at all. Now, we start adding code all over the place to make sure that we handle the closed case. So if you try to deposit something into a closed account, then we throw appropriately. And then we add new functionality to actually implement close. What happens if you have to close a closed account? Does it involve an error? Does it involve a warning? Should it even address it? There are concerns that we can then talk about that. And then we look at the problem from a slightly different lens, and we realize that actually part of the problem is that we're conflating several things together, right? I mean, I'm pretty sure that everybody understands that the code that I've written is not unfamiliar at all. Most of it's reasonable, we've all seen it, but we've had this problem. And part of the real issue here is that there we're conflating the existence of an object with its state, and persistence and all of the other stuff associated with it is actually now conflated into the existence into the service. So you have to deal with situations where the existence of a bank account is also an issue that you have to deal with when you're dealing with whether it's closed or not, right? And the reason for this is actually very, very good. In a typical NTR application, the repository does all of the saving and the save existing and so on and so forth. And the bank account object is just a piece of data. It lives somewhere in the database, and there's some repository system that pulls things out and gives it to us. And we need to actually have this architecture in order for us to provide state management for a high-scale system. But this is not actually how we started writing code. When we started, writing code in university, we talked about encapsulation and abstraction and object orientation, and how to make sure that just the related pieces of functionality were kept together. So, in some sense, we've kind of exchanged the elegance and the simplicity of the object-oriented model in order to obtain the real-world distribution and scale concerns that are there in the, when you want to write like a big bank. But of course, we're Orleans, and we've gone through the process of going back to using Orleans as effectively a distributed object store. So now if we actually switch it around and look at it through an object-oriented lens, the picture is a lot more familiar. We're actually able to see that we would write the bank account very cleanly as if it was an object, and for example, the maintenance of the is-closed state is now private to the object itself. And then we use the Orleans infrastructure to sort of do the object management piece behind it. And so far, again, none of this stuff is actually going to be unusual, right? So let's see what happens when we look to the next. So deposit, again, very clean, straightforward. All of the concerns are internal to the object. But actually, somebody's spidey sense should be tingling. Now, I apologize to the people who are red-green colorblind in this talk. Unfortunately, it didn't occur to me that red and green were particularly bad colors to display on a screen. But effectively, I've separated out the if is closed block in red, and if balance greater than 0 in green. And if you think about that for a minute, the red bit is actually going to have to be introduced into every single method in our object. Because the first thing we have to do is to make sure that only non-closed bank accounts can have operations occur to them. That's a bit of boilerplate. And so because of the boilerplate involved, people like me would actually look at it and say, that's a bit ugly. It's also a bit dangerous. What happens if somebody doesn't put that block in and they don't write a test to close the thing? You would still get all of the coverage that you need. Your coverage metrics would be met, but business functionality would not be actually safe. So in order to automate or to ensure that we have this boilerplate somewhere else, we actually ought to look at a different solution. Now, I want to just digress a moment and talk about the two pieces that we're trying to distinguish, the two pieces of the object. One is its actual affordance. What is an object going to allow you to do? And what is the object actually going to do itself? So between the affordance and the capability, we're able to actually look and try and see that the boilerplate stuff should actually be something that is defined as part of the object's affordance, and the capability should be the piece that actually addresses the business logic that you want to address in terms of, say, for example, crediting an account or debiting it, or so on and so forth. So if we now break up the object into these forms, you'll realize that there is a concept of a form where it is in zero balance, where it doesn't do anything, but it allows you to close the account. Or you can deposit some money in and put it into a positive balance state. Similarly, the closed form of the account doesn't have any affordance at all and has no capability. When a positive balance, when the object is in its positive balance form, you can deposit some more and that will keep it in its positive balance. But if you withdraw something from it, then depending on how much you've withdrawn, it could be in a zero balance state, continue to remain in a positive balance state, or go into a negative balance state. And similarly, in a negative balance state, we only allow you to deposit until you get to be in a positive balance state so that you can do something else. So if you now split the object's behavior into the affordance of the object and the capability of the object, it's starting to look like it's possible to model this problem as if it were really four shapes of an object. It's a shape-shifting object that could be in one of many forms. And that changes the way in which we actually look at the problem. So for example, we could be in a situation now where we can encode the information that we have into a kind of DSL that says, I have a thing called a bank account. I can give it an identifier. I'm interested in maintaining a balance, and I'm allowed to receive several messages. I'm allowed to receive a deposit message which may have an amount associated with it, a withdrawal message which has an amount associated with it, and a close message. However, the shape of the object will define which messages can actually be successfully accepted and consumed. And by going between the model of defining the objects in its multiple shapes, we can actually come up with a very strong and much less ambiguous way of specifying what the behavior of the object is going to be. And indeed, this form of representing the state machine isn't in any language that we know of. In fact, we have to define our own language in order to make this happen. And because we made a churn of stuff, we go off and actually build a system to do this. I'm going to digress just for a moment where we can actually talk about modeling choices and modeling subsets as types. And by modeling our system using these types, we are in a position to actually exclude the representation of incorrect behavior. So for example, if we modeled our system so that the only three messages we could possibly give are a deposit, a withdrawal, and a close, then it is not possible to even represent a new message unless we appropriately modify the definition of the state machine itself. And by doing so, we've actually eliminated a source of bugs that we wouldn't, basically it removes the amount of surface area that we have to test. Similarly, if we have a restriction that says, given the set of messages that we have, only these messages that are accepted in a given form are actually going to be processed in that form, then we can create a subtype that has just those messages in there. And then we're able to actually represent nothing other than the valid options, which fundamentally means that you don't have to write a whole bunch of boilerplate testing code to put if I'm in a closed state, do something different. We just eliminate that entire class of problems and eliminate that entire class of tests. We don't even have to write a unit test because the test will not compile. There's no way to represent the incorrect message. And we are going to basically do this by extending our type system And I have done so by actually providing a mechanism for doing union types and restriction types in C#. This is available in GitHub, and it's available as a V6 as well. This is already there out there, and I make use of this library in order to generate our code. So coming back to the shape-shifting object, what we want to do is make sure that each state that the object could be in is represented as its own interface and has only the messages that it represents, that it handles, be represented as messages in that interface. And each of the results, which is the restriction types, are actually their own type. So you can't even represent by copying and pasting a state transition that doesn't exist. And now we can go ahead and inject the capability. So really, what does it mean to deposit money into an active state? Well, it means update the balance by increasing it by the amount and leave it active. Similarly, when you want to withdraw money, subtract the amount and then decide if you're going to be in a zero state, then you go into the zero state balance state, and so on and so forth. So this code over here is now completely isolated and removed from the representation of the object itself, which means that I can unit test it. And it means that by ensuring that I have a specific type to represent the target state that I'm going to, I can't inject a transition from one state to another that doesn't show up in my definition. So by basically using a combination of types, a DSL for defining a state machine, some code generation, and a parser, we can actually generate a whole bunch of boilerplate code that does all of the infrastructure for us. And all we have to do is specify the capability, which is the only thing that isn't present in the state machine. And so what have we done? We've declaratively specified the state machine, derived appropriate types, which are very onerous to do by hand, incorporated the safety of the types into the system and eliminated entire classes of bugs and tests, decoupled capability and affordance, and then put a mechanism for injecting the capability into a system that doesn't need mocking, which means I can unit test it standalone. And more interestingly, just by looking at the state machine's DSL alone, I can make strong claims about the safety and behavior of the system. And I think that has enormous value, because you can expect somebody who doesn't have to actually decipher the code that is running in a system to figure out what's happening. You can make them do a little bit less work, and you can have people who understand the business context take a look at the DSL and be able to specify this. Now all this is well and good, but what does it have to do with Orleans? Well, Orleans is actually object orientation across machine boundaries with asynchrony built in. And because Orleans manages the objects themselves and has a mechanism for giving you the instance of an object by just providing its ID and do it at scale, well, Orleans is actually a fantastic way to actually implement the objects that we are going to build our state machines on. And so effectively, you can provide, we have a tool now that provides a partial class with the generated code, and then provide a partial class that allows you to write the capability of the behavior of the system in the partial that you have to handwrite. So you can generate the grains directly from the state machine and only provide the piece of functionality that describes the business logic. So in order for me to do this, I'm going to introduce you to the fact that the V6 actually already exists in the Visual Studio Marketplace, and you have to just install the V6 and the NuGet package, and I have already written a state machine file, And so I'm going to go ahead and show you that this whole thing is actually not smoke and mirrors. Can everybody see this on their screen? I'm going to just make it much, much larger, I think.
Yeah, we can see it really. Yeah, we can see it really well, John.
Yep.
Cool. Let's do 150%, and that will give us the whole state machine as we saw it. And what you do is you go in. Forgive me, I have already installed FSM for Orleans v6. But if you wanted to, you would basically. The only problem with this is that I have to restart Visual Studio a bunch of times, and I'm conscious of the time factor, so I don't want to do that. But effectively, all you have to do is go online and look for the FSM Orleans v6 and install it from here. Once you do that, you have a custom tool. So I've created a .fsm file. I've made its build action content, and I've set its custom tool to the Orleans state machine generator. And all I have to do is save the file, and it will generate the partial class for me with all of the types and everything built in. Now this will not compile, of course, because there's a bunch of stuff that is missing the rest of the project, for example, the amount type itself and the other partials. But if you notice that the closed state and the overdrawn state and the active state, these are all now implemented as a discriminated union type that allows you to use it effectively. So if we go down here to the active state, we can actually show you that, let me just see that. Oh yes, here we are. So you can look at the grains, and you can actually see how the code has been generated to handle deposit, withdrawal, and close. And the piece that's missing, of course, closed state machine handler, which doesn't exist yet. And you have to write the appropriate methods in that class in order for you to be able to inject it into the system. I apologize again that I don't have a full-blown demo that has some of this code already written, but this is effectively the simplest piece of work that you would have to do, and you've reduced the code that you would have to write to the minimum piece of specifying exactly just what it means to handle each message in each state. And you leave the state management piece to Orleans so that when you go off and actually ask for the grain, it'll actually allow you to do what you need to do. So that is the end of my talk. I acknowledge a few people here. I mean, apart from Sergey, who everybody knows here, and the Orleans community, there are people who've helped me with the F-sharp parsing and building the V6 and sanity checking the talk itself. And Scott Lashin, of course, who influences a great number of people in the F-sharp community by talking about how you can use type systems to actually make your code easier to represent and easier to reason about. And it's appropriate that I acknowledge him in this case. Microsoft, of course, paid for my visiting NDC London in order to actually provide the talk. So they're acknowledged as well. I will eventually be moving this into the Orleans contrib. That seems to be a much larger undertaking than I had given it credit for earlier. But for the moment, it's available on my own GitHub and it's in the Visual Studio Marketplace. So feel free to go ahead and use it and raise issues with me. Thank you.
Well, thank you very much, John. That's very interesting. I wonder how a functional programmer like yourself can bring themselves to write a DSL that uses the word "go to" in it. But I'll let you off. I'm not sure what Dijkstra would think.
So funny you should mention that. The word "go to" is somewhat unfortunate because in this case we're actually transitioning between states. And it's really an arrow between two states in a state diagram. I personally would prefer to use the word become. And Kevlin Henney, who gave me some good feedback about this talk earlier, also suggested the same thing. So it's entirely possible that in the next revision of the DSL, I would actually change that keyword from go to become. And if you think about that, that actually kind of makes sense. So, when you receive the deposit message, you become active, and when you receive a closed message, you become closed. And I think it reads well that way. But it is actually a very good point that you raised. The other point, of course, is that this whole thing is done entirely using functional programming. The project in question is actually entirely written in F# and uses fparsec to actually do the parsing and the code generation. The code generation piece is done using Roslyn, by the way, which also has a very strangely F# like wrapper around it in order for you to generate the code the way we wanted to generate it. So this is actually the parser for the language itself, and you can see that there's builders here that actually use F# to do a bunch of things, but that actually turns out to generate something like what it looks like, which is an arrow method that takes some parameters and whose body is effectively await the process message call. And this is effectively an F# wrapper around Roslyn. So I'm pointing this out because Ruben Bond and I have had several conversations about Roslyn and code generation and so on, and this might be of peculiar interest to him. I notice he's not actually on the call, but when he sees it, I expect to get a earful at some point about how I did something like this.
Yeah, I'm sure you will. Well, I'm curious to know what the original motivation was. Was it purely interest on your part, or was this solving a kind of business need that you saw?
So that's again an interesting problem. So amongst my other hats, which I talk through once in a while, I consult for a company that I used to own, and they have been starting to use Orleans for a bunch of things. And I found that when they were starting to build traditional NTR applications using Orleans and using the object model, a good amount of the effort seemed to be in order to translate what would have been business logic that went into a service layer into something that was basically boilerplate in Orleans. And if you're like me, semi-lazy and semi-skilled with writing code generators, everything looks like a code generation problem. And so I landed up actually starting to think of how best to actually represent this thing, and then see if we could actually use code generation to do stuff. But at this point, I realized that one of the things that Akka has with its actors is a state machine model that is not typed, and of course that obviously made it paramount that I used the type systems that I'm used to using in functional programming to actually extend and solidify the actor-based systems that we have in Orleans. And that's effectively the condensed version of how this went.
Yeah, thank you. I think it's really interesting. What got me thinking is whether it'd be possible to write an interpreter for your DSL, and then it wouldn't work quite in the same way. You wouldn't be able to perhaps generate the types in the same way, but you could potentially then have the DSL as a piece of state in the grain, and then update it on the fly. And different grains could have different state machines. Could be an interesting little side project.
we'll leave it to you to propose something like that.
Okay.
We should definitely have a further conversation. It sounds very interesting.
Yeah.
Another interesting issue that has been raised is that some state machines tend to be actually hierarchical in nature, and we really have no way of representing that with this naive type system approach. It'd be nice to see if we can extend that somehow.
Yeah, I'm sure there's loads we can do with it. Are there any other questions for John before we move on to Jacob? Any really difficult, hard questions to ask?
I rather suspect I've lost the audience at this point.
Yeah.
So it might just be you and me, Richard.
It might just be us, yeah.
You've already asked the hard question about GoTo, so
Okay.
we'll just leave it there, I think. Thank you. Thank you very much. I really appreciated the opportunity to talk about this.
No, thank you. Thank you very much for the presentation. I look forward to having a play with the code.
Cheers.
Cheers.
Actually, I have one additional question before finishing. I think this is a nice idea, and in fact, in some of the code I wrote previously, I was kind of doing a poor man's finance state machine, so I'm definitely fond of writing a lot less boilerplate code as here. But have you considered timers on like how they would be integrated in this kind of work? Because you were saying in Orleans it's easier because it's single threaded, but for example, you can make stuff reentrant, and specifically if you use timers, they will be reentrant. Like, are there any concerns there, or like not something that you looked at yet?
So the state machine is actually a static definition of what the flow control is going to look like. Now, the dynamics of a state machine's operation are entirely up to you. So I only say that you must, you can only receive these two messages in this state to become some other state. However, there is nothing that says that this has to be done only in terms of a message call or in terms of an external stimulus. There's nothing that actually says that your grain can't fire off a timer which then periodically sends messages. There's no way to represent the sending of a message in this state machine approach, but I don't think there should be any new concerns with regard to reentrancy and so on that don't already exist in terms of modeling your state machine this way.
Yep, that's fair. Good. Yeah, in fact, what I ended up doing, because these were like big objects with a lot of different states and a lot of logic, was just to, in most cases, I think in almost 100% of the cases, the timer would end up creating a message that was sent to itself so that it's handled in the right state.
Yes, absolutely. I mean, there's nothing that says, for example, that the deposit message isn't something that is periodically sent somehow. But based on the object's position, the deposit message could have very different operations. They may have the same exact capability, but the affordance of the object may change on receipt of a stream of deposit messages. Similarly, withdraw. So for example, I mean, it's entirely reasonable to have a system that sends a monthly withdrawal to a bank account, and you can still model the bank account's behavior this way, and indeed the state of the machine that is going to send the withdrawal message. It's just that I have not specified a mechanism here for sending a message. I've only specified mechanisms here for accepting and processing messages.
Yep, yeah, that's clear. Good. Thank you.
Any further questions? Okay, so allow me to finalize with one thing. I'm looking forward to Jakub's talk about event sourcing, because that's another issue that has been very dear to my heart for some time. And so I'm very pleased that he will have an extra 5 minutes to talk about that. Thank you.
Thank you very much. Let me share my screen with you guys.
Yeah, John, would you mind stop presenting? Thank you.
Give me a shout if you can see my screen.
Yeah, it's coming through.
Okay, so I just wanted to take 5 minutes of John's time and talk about how I'm using a stateless library for implementing final state machines in Orleans. Stateless is quite an old, mature, stable library for implementing final state machines. It supports some interesting features, and I've used it on multiple projects before, and currently I'm using it with Orleans. So I will be referring back to what John was saying during his presentation, and just trying to draw parallels between his approach and how I'm using stateless. So when John was creating the DSL for defining the state of the FSM and the possible transitions between those states, here with stateless, you just use C# directly, and you use the Fluent interface to configure your state machine. So you can specify your different states and transitions between them. And in that way you can build your state machine. So this approach uses just enums and the Fluent interface, and not a DSL. So if I can just quickly show you the just a sample code. The example that I have here uses a special offer which may exist in some retail business. So the scenario that we're trying to implement here is as the online shop, for example, you might want to create some special offers. You might want to implement some approval process for those special offers, and once the special offer is approved, it becomes active, and the customers can actually use that special offer. You might want to extend the special offer, or maybe expire the special offer early, and you may want to delete the special offer. So you begin by defining the possible states for the special offer. So we start with a draft. When the work on the draft has finished, the special offer is awaiting approval. When it's sent out for some approval, the special offer may be approved or rejected. If it's rejected, it goes back to the draft status. If it's approved, it becomes active. Now, once the special offer is active, it can be cancelled, or it can expire when it reaches the end date. And if you're working with the drafts, you might want to delete them. So those are the states of the state machine. And here we have triggers, which are basically the go-to words in John's example. So those are the possible transitions between the states. So I like to keep all my stateless configuration in a separate class. So it's all nicely encapsulated and separated from the rest of the code. So in here we are using the stateless classes to define our machine. We need to provide the field which will be holding our current state of the state machine, and then we configure individual states and the transitions between them. So in here, for example, we specify that when the state machine is in the draft state, what can happen is we allow the trigger request approval to change the state to awaiting approval. Or if we receive a delete trigger, we change our state to deleted. And then we carry on and we define, we configure all the states and the transitions between them in the same way. We can define the transitions based on some conditions. So, for example, we may use a permit if method that takes a function which returns a boolean to dynamically define whether the certain transition is allowed or not. So going back to John's example with the bank account, we may say that if the bank account is supposed to be closed, it can only be closed if the current balance is 0. So we may check here if the current balance is 0 and only allow this transition to the closed state if there's no credit or debit on that account. Over here, I just have one little helper method that uses a canFire method from Stateless to check if we can actually move from the current state to the one which is defined by our trigger. So this method allows us to check if we can transition according to the current configuration or not. Now, how are we going to use that? So we have an actor which is called a special offer. That special offer has a property which is our state machine, and it may have some other properties as well. As John mentioned before, I'm using event sourcing, and here I'm using a Olinka framework to help me with the event sourcing. But whatever I'm doing here, you can implement it in pure clean Orleans, even without event sourcing. So one little method which I have here, which I will use throughout all my actor, is the method that checks if we can actually change our status according to our current configuration. So it takes two parameters. It takes the trigger, the transition that we're trying to make, and it takes the event that describes successful transition. So, for example, if we need to expire the special offer and the expiration has been made successfully, then I will raise the event called special offer expired, which will have the state of expired against it. So we can, in other parts of the system, have event handlers that subscribe to those events and perform some other actions when that event happens. So as you can see here, I have events that relate to all the states in my state machine. So we have the event for special offer being approved, for example, that takes some string as the reason. You have the event for special offer being cancelled, deleted, and so on and so forth. Apart from events, we have a bunch of commands which basically trigger those actions. So if you're not using Olinka, using just pure Orleans, then instead of commands, you will just have your individual methods in your actor. So going back to our special offer, let's say that let's look how a submission for approval looks like. So when our actor receives the submit special offer for approval command, or the submit special offer for approval method is called, we just call our helper method handle status change, passing a trigger called request approval, and we're here providing the event that will be raised if the transition is successful. If the transition is not successful, then we're here throwing the exception that says why the transition cannot be made. you can have some generic exceptions here, or you can implement individual exceptions for different statuses or for different triggers. It's really up to you how you want to handle your errors. Here, for example, we have an example of the method that does some other validation before it even tries to change the state of the state machine. In case of the successful state change, we know that we've managed to successfully approve our special offer. We can carry on with doing some more work. So here, for example, I'm registering a reminder. So remember that Julian was asking about timers and reminders. And again, as John said, it really makes no difference. As you've used timers and reminders before, they just send another message to your actor, which will be handled. So if your reminder, for example, wants to change the state of your actor, then it will just send appropriate message, or call the appropriate method, and that will trigger the whole final state machine again. So there's no problem with using reminders. So in our example, we're using reminders to expire the special offer. So once we know what the offer end date is, we set up the reminder that is called automatically by the Orleans framework, and that reminder basically sends the command to expire the special offer, and then the normal processing of that command happens. So a few more examples for handling some other commands. Again, we just call our handle status change method, passing the appropriate trigger, and we return the event that describes what actually happened. At the bottom, we have the event handlers that update the current status of our actor based on those events. So all we're doing here, we're just setting the current state to the state that is represented by that event. So there is a one-to-one relation between the events and the states of the final state machine. So that's pretty much all there is to using stateless with Orleans. If you're not using event sourcing, then instead of raising all those different events and then handling those events in here, you will be just persisting the current state of your actor. So basically, after you successfully manage to change the state according to your configuration, you just persist the current state in your storage, and when your actor is activated again in the future, you'll just read your current state and set it, and that's all there is to use stateless. So I think that's all for me, unless someone has some questions.
Cool, thank you, Jacob. I assume you're using this on the solution you're currently working on.
Yes. I've used this on this project and also on some other non-Orleans project. I mean, stateless is quite a mature library, and it works without I didn't have any problems with it. You can easily configure quite complex state machines using different types of conditions. It has support for hierarchical states. So one of your states in your state machine may be actually a whole separate state machine which has a totally different configuration. So yes, if you need to implement that kind of logic in your application, I can definitely recommend stateless.
Cool, thank you. Any other questions before we finish up?
Oh, just a comment. I'm very pleased by the elegant solution you have there. It looks very good indeed.
Thank you.
Cool. Is there like an open source example we can have a look at for more information on how to use it with Orleans, or a blog post?
No, not really. I haven't created anything. If you need to know more, you can just come to me directly. I'm quite happy to share some code and guide anyone.
Cool. Thank you, Jacob. We've hit the top of the hour, so we'll wrap it up now. But thanks everyone for joining, and I'll publish this on YouTube shortly, so you can watch it again later. Thanks for joining us, and if you have any suggestions for things you'd like to present next time, or things you'd like to talk about, or hear from the core team about, then please drop me a note, or there's an issue on the Meetup repository, and you can put a comment in there. Thank you, and cheerio.
Thanks, Jacob.
Bye, everyone.